All right, so this is lab 3, constant speed. Okay, in this scenario, what we did is we took an air track, all right, put a car on it, put a little uh, flag on it that had a white dot, okay? We used a strobe light that flashed every zero point 0.1 seconds, and we pushed the car across the air track at constant speed, okay? That's how we ended up getting our information. Okay, so in this, the objective is to determine the average speed and distance traveled by an object moving with constant speed. You are going to do a graph of distance versus time, and it should look like this. You'll have an x-intercept where your first data point is. It's not going to go to 0. Okay. Then you're going to calculate the velocities of the lab. And when you do that, you're going to plot velocity versus time, and you're going to end up taking the area under the curve for a period of time that we asked you to. Okay, so that would just be that change in velocity. Well, it is the velocity; it's not changing; it's constant. But for that period of time. Okay. Now our apparatus is the photo. All right, and it says an acetate across here. What we had done was we took an acetate, and it's just basically a plus sign, and you lay it across the dots to make sure you're looking at where it appears on the ruler, okay, and the air tracking camera. Okay, so number 1, obtain the photo and the acetate crosshairs, align crosshairs such that the vertical lines across the edge of the leftmost point, horizontal situated as point as possible. All right, so this part you're just going to eye it up. What I suggest maybe doing is take a ruler and just hold the ruler perpendicular to the track and see where those dots line up as close as you can. Okay. It says record time t as 0. So the first dot that you're measuring is at time 0. That's why we have an x-intercept, because it's not at 0 centimeters. It's like whatever it was, 20, something like that. Repeat steps 2 and 3 for each point moving rightward in the photo. So you're going to go across all the pictures, and you're going to do that. I'll be honest with you. The next slide has the photo. I would actually print the photo off, lay it down in front of me, and then measure it. Because looking at it, it's going to be a little more difficult. Okay, if you have the possibility to do that. Record time in seconds, and for each point, increasing values 0.1 second intervals. Calculate the distance traveled from 0.2 to 0.5 seconds. So that's what this area is right here. So it's going to be the distance would be equal to x, which is distance 6 minus distance 3. Now, calculate speed using the interval halving method. Okay, so let me just show you something here. Okay? Let's say we have 10, 20, 30, and we have 5, 10, and 15. These are our 2 sets of data. Okay, let's see, so this is distance, this is time, and I want velocity. If I want to calculate the velocity here, I can't use this one here. It's not 10 over 5 is not the actual velocity. In order to find the velocity, you have to go one above and one below. So basically, velocity, the definition of velocity is change in distance over change in time. So the change would be the 30 minus 10 meters over 15 minus 5. So you have 20 over 10, which is 2 meters per second. Okay? So that's the interval halving method. So when you make your data chart, the first spot, you'll have an X. The last spot, you'll have an X. And when you have to do your LSQ, you're only using the set of data that falls between those X's. So you're not using the first row or the last row of distances times. Okay? And that's what all this means here, x n plus 1 and minus 1. All right? Calculate the average speed in centimeters per second, graph of distance versus time. Perform the LSQ and plot the best fit line. Plot graph of velocity versus time. Connect points with straight lines. Calculate the area underneath it. And then error analysis, your least count and your absolute error. Your least count is 0.1 seconds for the time, and the measurements on there are in centimeters. Okay, so it'd be 1 centimeter would be your least count, and the absolute error would be half of that. Do your LX. Actually, they only want the LSQ for the distance versus time graph, not the velocity versus time. Okay, so then you have to do this. So let me get out of this picture here and go to data. Yeah, here it is right here. So if you look, your first data point's at 39, okay? And then it's 47. And then this one's somewhere between 54 and 55. I would say 55. Don't estimate. Don't do 54.5 because you don't have that ability. Based on least count, the most accurate you can be is 1 centimeter, okay, on this map. So just keep doing that as you go across. All right? Have fun.